Hey, we're back for another section, section 10.1 from Susanna Epp's Discrete Mathematics. We're wrapping up the semester here with one final sort of general subject area, and that's graph theory. Graphs are, roughly speaking, abstract versions of networks. Anytime you've got a network of objects that are interconnected in some fashion, you can usually abstract that into what's called a graph, and we'll get into the details in a moment. Before I do that, just a reminder, if you're not up on the problem sets, make sure any past problem sets, I will accept them late. If you haven't handed any of those in, or if you haven't handed certain ones of those in, don't worry about the Moodle upload link. Just get it into me. I want to make sure that I'm seeing you stay up to speed with this class. That includes the exam. I might only be able to give you partial credit on the exam, but definitely get it in, even if it's late. I want to make sure everyone's staying up on this. If you're experiencing any issues, any circumstances that are preventing you from succeeding in this class the way you would like to, let me know. I am willing to be as accommodating as possible in that regard. My goal is not just to make sure you succeed in this class, but to make sure that you manage your lives through this trying period for all of us. So anything I can do to help you out, whether it's academically or otherwise, let me know. I'm here for you. Office hours, 9 to 10, Monday, Wednesday, always available by email, in whatever way you need to reach out to me. All right, wrapping up the semester. Section 10.1 introduces us to the idea of a graph. So a graph is a collection of two things, essentially, edges and vertices. And we'll typically denote, if we have a graph G, we'll denote the set of edges by E of G, and a set of vertices. And the singular of this, by the way, is vertex. So you don't say vertexes, and you don't say vertice. Although I hear a lot of people, when you get used to saying vertices, people will just kind of default to saying, this vertice, no. It is a vertex. It is a vertex. It is many vertices. All right, so vertices plural, vertex singular. Vertices of a graph G are usually denoted V of G. And I'm going to draw a lot of pictures. I'm not going to write a lot of words down. You can read the words in your textbook. Graphs, by the way, this is the subject area that is at the center of my research in mathematics. I do research in graph theory, specifically related to what's called the independence polynomial of a graph, and I'm happy to talk to you about that if you're interested outside of our normal class. I'm happy to talk to you about independence polynomials and how you could get involved in cutting edge research on them. Seriously, it's really quick to get you to the cutting edge in this area. Anyway, graph theory lends itself very well to pictures. So there are a lot of words in the book, lots of terminology dealing with graphs, but I'm going to draw a lot of pictures to kind of help you understand what it looks like. So you've got edges and vertices. Like I said, generally speaking, anytime you have a network of some sort, websites connected by hyperlinks, cities connected by highways, social networks, people connected by affinity of some sort, if they're in the same social circle, if they know each other, if they're acquaintances, and so forth. Anytime you can take objects and relate them to one another in some fashion, two objects related, whether it's through connection or correspondence or acquaintance, anytime you have that kind of structure going on, you, my friend, have a graph. So, graphs are usually very visually presented to us. So we might have something like this, where the dots that I've drawn represent the vertices. So in this particular graph, I've got 1, 2, 3, 4, 5, 6 vertices. I'm just sort of labeling them arbitrarily. And I also have edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I got them all 9 edges. Again, I've just sort of labeled these arbitrarily. So you can have multiple edges between two vertices. You can have edges that loop back, that start and end at the same vertex. Some of the language we use to describe edges and vertices is to talk about the endpoints of an edge. So for example, the endpoints of, just to pick an edge over here, of the edge E5 are V4 and V3. I'll write them in the opposite order that I said them, just because I like numbers to go from smaller to larger. So the endpoints, if we want to talk about the endpoints of E5, we talk about V3 and V4. Your textbook talks about an endpoint function, which assigns to a given edge the two, or perhaps one in the case of a loop. Notice that the only endpoint of E4 is V2, so you can have what are called self-loops. The endpoint functions assign to a given edge the one or sometimes two, generally two, vertices that serve as the endpoints to that edge. Your textbook also talks about loops, so this is an example of a loop. It talks about parallel edges, so right here we've got parallel edges. Two edges are parallel when they run between the same pair of vertices, or even two self-loops. You can talk about having, if we had another loop here at V2, then that loop and E4 would be parallel to one another. You talk about adjacency. So V4 and V3, for instance, note that V3 and V4 are adjacent vertices. I'll get lazy sometimes and write VXS for vertices. They are adjacent vertices because there's an edge between them. And we saw that relationship reflected a different way when we said that the endpoints of E5 are V3 and V4. Another way of saying that sort of highlights the vertices rather than the edge is to say that V3 and V4 are adjacent because they share edge E5 in between them. A self-adjacent vertex is one lying at the end of a loop. So V2 is self-adjacent because it has a loop that goes back from V2 to itself. We talk about incidence. Yet another way of relating this edge E5 with vertices V3 and V4 is to say that V3 and V4 are incident on E5, or to say that E5 is incident on V3 and V4. That terminology is sort of reflexive or symmetric in that sense. You can talk about adjacent edges. Just like V3 and V4 are adjacent vertices because they share an edge, you can talk about, for instance, E5 and E9. E5 and E9 are adjacent, squeaky marker, edges because they share a vertex in common. So anytime two vertices have an edge that connects them, we say they're adjacent. Anytime two edges have a vertex in common, we say they are adjacent. We're going to talk about isolated vertices. I'm going to add one over here. 6 vertices to begin with, so I'll just call this one V7. Just add another vertex sort of dangling off on its own over there. This guy is isolated because it is not connected to the rest of the graph. It doesn't share any edges with the rest of the graph. It would no longer be isolated, by the way, if I added yet another vertex, say V8, and I connected it to V7. It would no longer be isolated in that case. Forgive me looking at my notes a lot here. There's just a lot of terminology, but really I like to focus on the intuition of graph theory, which is what makes it such a beautiful field for study, because you can get really, you can grasp most of the important concepts visually, and it's really quick and easy to understand those principles and get you literally to the front lines of research. I do research in an area where if I sat down with any of you for 3 or 4 hours, I could get you ready. I could teach you the rudiments that would get you to the point where you could begin to ask questions, open questions that have not yet been solved about graph theory. You would have some means of approaching solutions to those questions. I'm not saying they're easy questions. You probably wouldn't be able to solve them right away, but you could begin asking those questions really easily, and you'd understand them. So again, focus on the picture, and the words will come. The words will come. Don't worry so much about the words at first. Focus on the intuition. there's this idea of isomorphism between two graphs. So iso means same, and morphism essentially refers to a form. Morph is like a form or a shape. So when we say two things are isomorphic, they have the same shape. An isomorphism between two graphs, I'm just going to draw it. I'm not going to do the technical words, blah, blah, blah. You can read that in the book. An isomorphism between two graphs essentially means they have the same picture. The same shape. So for instance, I could draw these two, this graph here, rather, and I'm going to use that little symbol to denote isomorphism. And I could say, well, I could draw that in a slightly different way if I wanted to. Notice both of these graphs have the same number of vertices, and they're sort of interconnected in the same way. Even though it may not look like it at first pass, all I'd have to do is to take this little inside triangle and flip it up to make this picture look almost exactly like that one. Maybe with a little resizing. The idea is that these edges, these lines I draw to represent the edges, are really malleable. They're really flexible. I could stretch them, I could compress them. I can actually make them cross over each other. I chose not to do that in this picture over here, but there's nothing stopping me, if I really wanted to get funky, with taking an edge and crossing over. Maybe that's my new E7 right there. I haven't changed the graph. It's the same graph, but I just chose to be kind of funky with that one edge. You can draw the edges in any fashion you want to. They can even cross over each other. Just means that it's not a planar graph. It's not drawn in a manner that can be put in a plane without crossing of edges. Anytime you have an edge going like this, it's important to note, by the way, that those intersection points between the edges are not vertices. They just happen to cross pictorially there. As we saw a moment ago, I can shrink that edge down and draw this in a fashion that is planar. It makes it clear that you can draw it without an intersection. Anyway, that would be a move I could make that would make an isomorphic copy of that original graph. It looks a little different, but it's the same graph, just like these two down here. Technically speaking, as your book will tell you, two graphs are isomorphic if there's a way of corresponding the vertices of one graph with the vertices of the other, and the edges of one graph with the edges of the other, so that the endpoint functions are preserved. So that if you've got an edge over here with these two endpoints and you carry it over here, then the corresponding edge has the corresponding vertices as endpoints. So that's all discussed a little more technically in the textbook. I'm not going to get into details here. One thing we haven't talked about yet is creating a directed graph. All of the graphs that I've drawn so far are undirected in the sense that the edges don't have any direction to them. They're just edges. They're just hanging out between two vertices. It's a line segment, to be precise, between any two vertices. But what if I wanted to add some direction to those edges? And what I mean by that is just to indicate maybe there's a natural flow. This is really helpful for indicating, for instance, if you want a graph to represent a highway, a system of highways or streets, there are such things as one-way streets. So maybe flow is only allowed in one direction. So a directed graph, or for short, digraph, people will say digraph, is one in which you've got your edges and your vertices, and maybe that guy's connected there, maybe there's a self-loop there, and maybe even some parallel edges. I'm not even going to label them because the labelings aren't so important. But for every edge, you have the additional property that it has some direction to it. So every edge is not just indicate the two vertices that work, or in some cases one vertex, that serve as endpoints, but also there's a flow to it. You can only go a certain way on the graph's edges. So this edge only points, for instance, from vertex U to vertex V. E goes from vertex U to vertex V and not from vertex V to vertex U. Incidental, like an edge incidental vertices. Incidentally, that's where the endpoint functions come into play. You can go back and look at the details in this section of the book, but you distinguish very clearly between the initial vertex of an edge and the terminal vertex of an edge. The initial vertex is where it begins, and the terminal vertex is where it ends. And that really only makes sense in the context of directed graphs. I've already mentioned a few examples: the internet with websites interconnected by URLs, cities connected by highways, molecules. You can talk about the atoms in a molecule where the bonds between the atoms are the edges. Kinship networks. We talked about social networks. Kinship networks are all actually used in anthropological contexts where you're looking at the patterns of familial relationships between people in the same household or the same family. I've got just a couple more concepts I want to talk about, some special kinds of graphs, and then we'll do a quick example and end this section with a quiz. A couple more pieces of terminology. A simple graph has no loops and no parallel edges. So neither of the graphs I've drawn so far, neither the graph on the other side nor this graph here, this directed graph, are simple because in both cases there is a loop and there's a pair of parallel edges. But if you have a graph with no loops, no parallel edges, you're called a simple graph. A complete graph, whether you are directed or not. Generally speaking, though, you're talking about undirected graphs. A complete graph is a simple graph with as many edges as possible. And that means that there's an edge between any pair of vertices. That would be what it would mean to be as many edges as possible and still be simple, right? To have no loops. So any pair of, to be precise, I should say, any pair of distinct vertices, because we don't want loops. You give me any two vertices, I better see an edge there, because otherwise I don't have the maximal number of edges. But a complete graph, usually denoted Kn, where n is the number of vertices that appear in it, will be one in which, this is K2, one in which the most number of edges appear. In other words, you have an edge between any pair of vertices. There's K3, K4, if I have 4 vertices, I want to connect any pair of them and so forth. You could do this all day, babe. You could do this all day. Just go ahead and draw these complete graphs. A bipartite graph is one in which all of the vertices can be divided into two groups, two subsets of vertices. Let's call them U and V. And the graph has the property that the only edges that occur are edges that cross, I'll add another one there, that cross from U to V. All edges are in the middle here. All edges go from U to V and not between things in U and not between things in V. It's often very hard to recognize if a graph is bipartite because notice I don't tell you what U and V have to be. To show that a graph is bipartite, you have to come up with a U and a V that puts all the edges in between those two sets. And it might not be an obvious choice of U and V. A special kind of bipartite graph is called a complete bipartite graph. And I'll just draw a simple example here. A complete bipartite graph is one in which you've got your U and your V, so you're bipartite. It's not the same as complete because in a complete graph, you want edges between all pairs of vertices. But in a bipartite graph, you're only allowed to put the edges between a vertex in U and a vertex in V. But what I want for a complete bipartite graph is that you have as many edges as possible, which means every vertex in U is connected to every vertex in V, is adjacent to every vertex in V. Does that make sense? It's not quite the same thing as complete, where you would have every possible edge. It is a bipartite graph. It's a bipartite graph in which you have as many edges as possible while still being bipartite. And that means all the edges that go from U to V must be present. So that's a complete bipartite graph. Now your textbook also talks about this idea of a degree of a vertex. I'm going to go back to the example on the first half, just to be a little more efficient here. I'm going to go back to the example on the first half here to talk about the degree of a vertex, which is denoted by d of v. And the idea is to look at the number of, declutter this picture a little bit. The idea is to look at the number of beginnings of edges. So we don't want to count the edges. So for instance, v2, well, let's start with something that's a little easier. Let's look at v1 first. Imagine drawing a little circle around v1 and standing there, and you can't see the far off ends of the edges that begin in v1, but you can see where they start. They're starting right at your feet. Imagine yourself standing right here. You can look down that edge, E1, you can look down that edge, E2, and to your perspective, from your perspective, you see two edges leaving V1. So we would say the degree of V1 is 2. We would say that the degree of V3, we see 1, 2, 3, 4, 5, 6. We see 6 edges if we're standing at V3. We see what? E2, E3, E9, E8, E7, E5, starting out of V3. So we would say the degree of V3 is 6. So it's the number of starts to edges, technically you call it the germ of the edge, I don't think your book uses that term, is the degree of a vertex. In some sense, it tells you how many edges are at a vertex, where if you have a self-loop, you count the edge twice. So for instance, looking at V2, this is a little trickier. We see 1, 2, 3, 4 edges leaving V2. Now, imagining that this loop, E4, is way off in the distance, and we can't see how it loops back around, we just see it, if we're standing here at V2, we see it as though it's 2 distinct edges. We count it as though it's 2 distinct edges for the purpose of degree. So the degree of V2 turns out to be 4. Any self-loop, any loop at V2 or at a given vertex, we count twice. So every loop counts twice, every other edge, whether it's parallel or not. Notice that we had parallel edges down here, it didn't matter. Every edge that isn't a loop counts once for the degree. So that's how you define the degree. Like I said, it's kind of like how many edges seem to lie at a given vertex. And there's a very handy formula that I'm going to write down. Let me go ahead and erase. And we'll look at this formula that relates what's called the total degree of a graph with the number of edges. And you can already kind of see the intuition. A formal proof requires induction, and I think your textbook actually goes through that proof. Sorry, that wasn't COVID, that was me inhaling this really awful cleaner fluid for whiteboard. A formal proof of the theorem I'm about to write down, which is actually one of the most important from graph theory, as simple as it is. A formal proof requires induction, and I encourage you to take a look at the textbook to see how it's done by induction. You would induct on the number of edges in the graph. Take that as your n and look at a base case, blah blah blah. But an informal proof, I think, is just as important. What I'm going to do is just draw. There we go. Here's a graph here. Notice that no matter what we're looking at, whether it is an ordinary edge like E1 here or a self-loop like E2, every edge in the graph contributes to ends to the graph. So by end, I mean I've got this end to E1 and I've got this end to E1. There are 2 endpoints corresponding to E1. E2, the 2 ends, I don't want to, it's not a directed graph, I don't want to imply that. If we were to zoom in on this vertex here, call it V, V serves as both endpoints for E2. And just like we saw a moment ago, the way we count degree on the, was that? No, I'm sorry, just what I just erased. It's not on the other side, so I just erased it here. The way we were counting degree, we were counting the ends of edges and not the edges themselves. So in that sense, each edge contributes to I'm going to call them informally, as I have been, edge ends to the graph. And each vertex contributes degree of vertex edge ends, using that same informal term. The way we counted, I just erased it, but the way we counted the degree of a vertex was to tabulate the number of edge ends lying at that vertex. So each vertex V, contributes d of v, the degree of v edge ends, whereas each edge contributes 2 edge ends, because each self-loop even contributes the 2 ends, even though they're the same vertex. So what this says, whether we count them by tabulating the edges, or whether we count them by tabulating the vertices, the number of edges in a graph times 2, because each one contributes 2, must be equal to the sum over all of the vertices of the degree. So this is a theorem, I don't remember what your textbook calls it, but this is a pretty powerful theorem in graph theory, as simple as it is, to say, well, adding up the degrees of all vertices gets you the same thing as adding up the size of all the edge sets, or the size of the edge set, rather, times 2. Because every edge in the edge set contributes 2 edge ends, whereas every vertex contributes d of v edge ends. Whether you count edge ends over the vertices or you count them over the edges, you get the same answer. Again, there's a formal proof of this using induction, inducting on the number of edges in your textbook, and I encourage you to take a look at that. But for now, I'm just going to leave that as it is. And if you haven't done so already, please pause the video and make sure you're understanding any of these terms. If any of the terms are unfamiliar to you, you're still not comfortable with them, you want to ask me questions about it, shoot me an email, ask me questions. I'm happy to answer them. We're just going to look at one example. I'm going to check on the time, the running time. Yep, we're at about 27 minutes for this video. I don't want to take too much more time. That is like record time for getting through all these terminology. So props, high five, fist bump, whatever y'all want to do. Actually, I was doing that to here. I'll do it to the camera. There we go. Fist bump, high five, whatever you want. Kudos to you for getting through all that terminology. Let's look at an example here of a graph. Example: let G be the set. Let V of G rather. I'm going to define the vertices. So the graph I'm about to define, the vertices are the set 1, 2, and so forth. All of the whole numbers, all the integers from 1 to 12. And E of G have an edge if U does not equal V and either U divides V or V divides U. Let's see if we can get a picture of this graph to start with. That's the first question, is can we get a nice intuitive picture of this graph? So we've got the vertices are the integers from 1 to 12. And I'm going to draw them in a very suggestive fashion. 1, 2, 3, 5, 7. So far I've got 1, 2, 3, 5, 7, 11. Can you tell which numbers those are? What numbers am I missing? I'm missing 4, I'm missing 6, I'm missing, what else? 1, 2, 3, 4, 5, 6, 7. I'm missing 8. I'm missing 9. I'm missing 10. I've got 11, and I'm missing 12. All right. So those are the vertices in the graph. Now we have to figure out where to put edges. There's going to be an edge if either U divides V or V divides U. So look at any pair of vertices and figure out when to put an edge between them. I'm going to use red. I haven't used red at all lately. So obviously there's going to be a lot going on at one vertex in particular. 1 divides everything. Maybe I shouldn't use red. Oh, I missed. missed the vertex for 8. There we go. 1 divides everything. So you better have an edge going from 1 to everything. 2. Let's just go in order here. 2 divides, well, 1 divides 2. We've already got that. 2 divides 4. It also divides 6. It also divides 10. Also divides 8. Also divides 12. So we got edges there. 3. 1 divides 3. So we got that already. 3 also divides 6, divides 9, and divides 12. We could go in order by size or in order by this graph. Let's just go in order by this graph. 5, 1 divides 5, but 5 also divides 10. 7, 1 divides 7, and 7 doesn't divide anything else, at least in this graph. So we're done with 7. We're done with 11. 4, we've got 2 dividing 4 already. We've got 1 dividing 4 already. We also have 4 dividing 8 and 4 dividing 12. 6, we've got 1, 2, and 3 dividing 6, but 6 also divides 12. 9, we've got 3 and 1 dividing into 9, but 9, like 7 and 11, doesn't divide anything bigger. 10, same thing. We've got 1, 2, and 5 already connected to it, but it doesn't divide anything bigger. Same thing with 8, same thing with 12. I think we're done at this point. So this is what's called a divisibility graph, and it indicates almost like a hierarchy between the numbers. Notice I put the primes one level up from 1, and I put the products of 2 primes, not necessarily distinct, next, and then I put the products of 3 primes, not necessarily distinct, above that. That gave me some way of sort of ordering these. A couple quick questions about these, and then I'll give you a quick quiz, and we'll call it a day. Find the degree of each vertex. Which vertex has the highest degree? Which one has the lowest? I'm going to leave it to you to find the degrees of all of these, but it's pretty easy to see which one has the highest degree, and that's going to be 1, because 1 is connected to every other element, and because there are 11 elements not equal to 1, the degree of the vertex 1 is 11. The lowest degree would be those that are divisible only by 1 and don't divide anything else, and it looks like those would be the lowest. 7 and 11 both have degree 1 because 1 is the only thing they connect to, the vertex 1. Sorry, the notation is not perfect. This 1 refers to the vertex 1. This 1 refers to the number of elements connected to 7 and 11. How did we ensure? So I'm just reading off some questions here. Again, find the degree of all of these. In fact, let's say quiz CE10 is find D of V for the others, for the other vertices. You've got 9 other vertices here. Go ahead and make sure that you can find the degree of those vertices for the remaining ones. That'll be your 10th quiz. Just ask a couple other questions about this. There's from my notes here. How did we ensure that this graph has no loops and is therefore simple? Well, we only draw one edge between any 2 distinct vertices, so there aren't any parallel edges. And there was one stipulation I made over here that made sure we didn't have any loops. Notice, if I had divisibility, a number does divide itself, because any number n can be written as n times 1. So n equals n times 1, which means that 1 divides it. That n divides itself, rather. So every element is divisible by 1, but also divisible by itself. So if I didn't make this condition, I would have had loops all over the place. Every single one of these elements would have had a self-loop if I hadn't made this stipulation. So this is the condition that made sure there were no loops in the graph. And finally, I'm asking us to find the greatest distance between 2 vertices in this graph. And the question there, we haven't talked about distance yet, but it's a pretty natural idea. The distance between 2 vertices is the least number of edges that you can take to chain from one vertex to the other. So if I start here and I want to get to that vertex and it takes me 1, 2, 3 edges to get there, then my distance would be 3 between those 2 vertices, assuming there was no quicker path. Maybe there's a single edge that connects the 2. If they're adjacent, the distance would be 1. In this graph, I think the diameter, or the greatest distance between 2 vertices, is going to be 2. And why is that? Because we already saw 1 connects with everything. No matter what, you can always connect any of these elements, even the ones that are connected only to 1, like 11. You can connect from 11 to 8 by passing through 1 and going there almost directly. So the distance between any two elements in this graph, distance between any u and v is 2 in this graph. And we would say that the graph has diameter 2, the diameter being the greatest distance between any two distinct elements in the graph. That's a lot. This section 10.1 of your text, is not a particularly hard section. I hope most of these ideas are pretty intuitive, but there's just a lot of ideas thrown at you. And as I said earlier, please let me know. Any of these terms don't make any sense, come by the office hours, Monday and Wednesday mornings, 9 to 10. Shoot me an email. I'll find another time to meet with you. Just ask me questions by email. Check in with the Math Lab. And again, quiz CE10, which I'll post on the website shortly, on the Moodle site shortly, is to find the remaining degrees here, any of the ones we didn't compute already. It's everything but 1, 7, and 11, I guess. Thank you so much. I'll be in touch with y'all. Keep working hard, and I can't emphasize this enough. Work with each other, work with me, and if you need to turn in something late, better late than not at all, so turn it in whenever it is that you get it done. Thank you so much, and I'll talk to you soon.